Welcome. This is Nathan Weezy from Marquette University. This class is Digital Control Power Electronics. In this section, we're going to talk about the control design for a current mode controller of a boost converter in continuous time. So we have our general structure here in black for a boost converter. We have V in, the inductance L, C, the capacitance, the output capacitance, R, ESR of the capacitor, and our output load resistance R. And in blue, we have our generalized control structure, where GC of S is what we're trying to design in this section, which is our controller. Typical current mode type control, we have a comparator where we're measuring the current and we're comparing that to a current command, IL of star, let's say. So our controller is going to generate the current command, how much current we would like to pass through the inductor. Now, how does this all work? We can generally sketch this out briefly here. We're going to have an S signal for setting, a reset signal, and then we're going to have the output of we're going to have the current command stuff. So what happens in terms of the set signal, that's generated from a continuous pulse generator, which at time TS always generates a small, really thin pulse, let's say less than 1%, and this happens indefinitely. And what that will actually do is generate Q, or turn on the SR latch. So right when set hits, Q will go to 1. Now, how do we actually reset the thing? Well, that is done through the comparison of the actual inductor current and the current command. So here in this green, let's sketch IL star. That's what we'd like the current to be through the inductor, and then in purple we'll sketch IL. So right when we set, we actually are charging up the current through IL, so it'll start linearly increasing until some point it'll hit here. It'll hit the command. Once it hits the command, the comparator will pulse out a 1. In other words, that's a reset because the output of the comparator is connected to the reset. When that happens, the switch will turn off, the inductor will connect to the output. Of course, the current will start ramping out. And this will then again complete a cycle and then start repeating. So the pulse generator will pulse a set and the switch will turn on until IL hits the actual commanded current, and we generate a reset signal, and the switch will turn off and the current will start ramping down again. And so this is the basic structure for the current mode control using a comparator, a SR latch, a pulse generator, and a controller. So kind of understanding that basic block diagram, all we really have to do now is design the controller. Essentially the controller will take the error of the voltage and generate IL star, how much current we actually need. So we're going to talk about all this in terms of MATLAB. This is going to be our boost converter parameters here. And then we're going to define the plant transfer function right here. And where this comes from is a basic power electronics course. And they derive the plant transfer function. We're essentially going to be consumers of that function. We're not going to talk about how it's derived, but essentially we're just going to use it. Let's do some highlights here. If we look at this, we have one pole right there, and up top we have a 0 that's in the right hand plane, and then we have another 0 due to the ESR. So we have an ESR 0. We have a right hand plane 0, which will be tricky to get rid of or work with, and then we have one pole. Alright, so this is just, we're going to plot this in Bode stuff and take a look at this. This is our controller design parameters here. So we're going to select our gain, or excuse me, we're going to select our bandwidth or phase margin, and that will determine where the poles and zeros go. Now with current mode control, we use one pole, 1, 0, 1 integrator. So our controller is going to look like line 45, line 45 here, which is our controller. And all the work to design this is similar to the buck converter design, or we're using the K-factor approach. So once we have selected our control design parameters, essentially we need to find where the pole and the zero are, and we do that by getting the gain and the phase of the transfer function at the crossover frequency, which is line 35. Then we calculate how much phase boost we need from the controller in line 36, the gain we need from the controller in line 37. 38 gives us essentially what K boost is, that ratio is how far apart the poles and zeros are to give us the proper phase boost. And then essentially 39 through 43 gives us our controller integrator gain and our pole and zero location. So once we go ahead and complete that, we're going to do that design here quickly. You can run this script, you can copy and paste it. This is what we get for our controller design, or excuse me, I'm sorry, this is our plant, given those parameters up above. And this is our controller, the basic structure of it. We're trying to find K, omega Z, and omega P. If you run the script and do the design for this, what you're going to get is one pole, one zero, and one gain. And there is a slight mistake here. These squares should not be here, which is highlighted in line 45. There are no squares here, so that is a mistake. Just disregard that. Those squares are not there. We have one pole, one zero, and one integrator in current mode control. So those are our poles and zeros and gain in line 3, equation 3. Line 4 essentially gives us our pole locations for our closed loop system. And if you look at them, they're all on the left-hand plane, which is something that we generally desire in order to ensure stability. So that's good. So let's go ahead and take our Bode plots and take a look at them in terms of the plant transfer function, etc. GP is our plant. You can see we have a fixed gain. We have our pole, and then we have our two zeros, which is interesting here because what happens with the boost converter in current mode control is the gain actually starts going back up this way, which is really bad because generally at high frequency you want to roll the gain off at least at minus 20 dB per decade so that you don't run into any stability issues. Okay, so we can take a look. We designed this for 1 kilohertz. Our gain, this is about 1 kilohertz here. This was our gain of our plant, and then our controller is this, and you can see that we're centered around 0. So if you add those two together, that'll give you a 0 dB at 1 kilohertz. So that'll force our transfer function our open loop transfer function to cross over there, which is this orange. You can see it crosses over right at 0 dB, which is perfect. Now, if you go ahead and calculate the closed loop response, which is GOL over 1 over GOL, you actually see you have a nice damped response. This is probably one of the better responses that we've had. But what you also see here is that the gain drops down to, I don't know, minus 30 dB and then just stays level even up to high frequency. So that's something interesting. It's not continuing to go down like a low pass filter. Something to consider here when you consider the boost converter current mode control. In terms of phase margin, we can take a look at that. GOL, let's see how far we are away from minus 180 here at 1 kilohertz. It looks like we have this distance here, which is approximately 60 degrees, which is what we're looking for. Again, this isn't wrapped properly because of the way MATLAB output it, but is indeed 60 degrees away from minus 180, which is exactly what we'd like. Okay. Let's take a look at the output response of this boost converter in current mode control. Again, we are stepping from 10% step of load up to 100% in this case. And you can see that we have generally a first order response for the voltage. So it starts dipping here. You can see our control actuation goes up here and stays up to this. Remember, this is no longer D. This is actually the current. This is IL star, if you will. This is how much current we'd like to flow. And you can see that IL and the U signal here are tracking, meaning if you lay them on top of each other, the peak should hit exactly where IL star is. So if you have this peak here, it should match this. Okay, the other thing you can see is that this recovers in, let's call it, although this is 1 kilohertz, you'd expect it to be here. It's not exactly there yet in terms of voltage. The current is getting up there in easily enough time, but response time is more like 2.5 millisecond here before it gets up. But I like, in general, current mode control is more desirable. I mean, not always, but it's nice because you're directly controlling the current. So you generally have a nice first order type response. And generally, unless you make it unstable, you don't have any ringing, which is good in terms of response time. Okay, thank you for taking a look at current mode control of a boost converter. This concludes this section. Thank you.